My name is Don Mercer. In this video, we will be looking at sample drying calculations. Financial support for production of this series of video presentations was provided by the Széchenyi Society, founders of the Hungarian programs at the University of Toronto. The Széchenyi Society's sponsorship is gratefully acknowledged. I would personally like to thank Dr. Ph.D, professional engineer and fellow of the International Academy of Food Science and Technology, who is a professor in the Department of Chemical Engineering and Applied Chemistry at the University of Toronto. Dr. Ph.D.'s considerable efforts in coordinating this project are greatly appreciated. The material in these video presentations is based on an e-book published in November of 2014. Its title is An Introduction to the Dehydration and Drying of Fruits and Vegetables. It is available on the International Union of Food Science and Technology website, which can be accessed at www.FIAFoST.org. We will be examining sample dryer calculations and close with some summary comments. In sample calculation number 1, you are asked how much product at 10% wet basis moisture would you obtain from drying 3.5 kilograms of carrot slices with an initial wet basis moisture content of 89%. In addition, we have to find out how much water would be removed during the drying process. The problem has been defined for you, but you need to ask yourself whether or not you understand what it is actually asking you to do. If so, you can begin by drawing a diagram of the system. Here is a rectangle representing the dryer. Going into the dryer, we have the feed material, which consists of 3.5 kilograms of carrot slices with a moisture content of 89%. Coming out of the dryer, we have dried carrot slices with an unknown weight that we will designate as being X kilograms and 10% wet basis moisture. We also have water being removed. However, we do not know the amount of water, so we will let this be equal to Y kilograms. So where do we begin? Usually it is best to start with what you know about the most. Here, we really only know about the feed material going into the dryer, so let's start there. The weight of the water in the feed material is 3.5 kilograms times 89% water as a decimal fraction, and this tells us that we have 3.115 kilograms of water in the feed material. Throughout these calculations, I will be carrying extra decimal places, so please do not get too hung up on this or the number of significant digits. The percent solids will be equal to 100% minus the 89% water, which leaves us with 11% solids. The weight of the solids in the feed is going to be equal to the weight of the feed material, 3.5 kilograms, times 11% as a decimal fraction, and that gives us 0.385 kilograms of solids going into the dryer. So we can now put these values on our diagram, and they will be shown in the bottom left-hand corner in red. Establishing the next relationship may not seem all that obvious at first. In drying, only moisture is removed, and perhaps there are some other volatiles that may be removed as well. No solids are lost unless they are blown out of the dryer, or perhaps they may even catch fire in extreme cases. However, this is usually not what occurs. Therefore, we can say that the weight of the solids going into the dryer in the feed will be equal to the weight of the solids coming out of the dryer in the product. Although it seems so simple, it may be something that is forgotten in the problem-solving process, and this is a pivotal step. If there is a loss of solids, you will need to incorporate it into your solution. So this tells us that the weight of solids in the product will be the same as the weight of solids in the feed. Therefore, there will be 0.385 kilograms of solids in the product. We can add this information to our diagram. We will show this in the bottom right-hand corner in red. We now know that there are 0.385 kilograms of solids in the product and that the product contains 10% water. If the product contains 10% water, it will then contain 90% solids. Remember that you only have solids and water to worry about in most drying problems. Letting the weight of the product be X kilograms, we know that 90% of this amount is solids. We also know that the weight of these solids is 0.385 kilograms. This tells us that 90% of X, or 0.90X, will be equal to the weight of the solids, which is 0.385 kilograms. Solving for X, we see that X is equal to 0.385 kilograms divided by 0.90, which is equal to 0.428 kilograms of product coming out of the dryer. If we have 0.428 kilograms of product and 0.385 kilograms of this is solids, the difference between these two values must be water. The weight of water in the product will be equal to the weight of the product minus the weight of solids in the product. We can then substitute the numerical value of 0.428 kilograms for the weight of the product and subtract 0.385 kilograms of solids, which gives us 0.043 kilograms of water being present in the product. And now we can add this to our diagram. And once again, the information is shown in the bottom right-hand corner of the diagram in red. Looking at the diagram, we can see that we have 3.115 kilograms of water in the feed material and 0.043 kilograms of water in the product. Now we have to find the value of Y, which is the weight of water removed, so we will use a mass balance approach. The weight of the water removed is going to be equal to the weight of the water in the feed minus the weight of water in the product. Repeating this equation, we can now substitute the value of 3.115 kilograms as being the weight of the water in the feed and subtract 0.043 kilograms of water in the product from it to get 3.072 kilograms of water being removed in this drying process, and that's approximately equal to 3.07 kilograms. Therefore, the weight of water removed, which is the value Y, is equal to 3.07 kilograms. There is also another way to find the weight of the water removed. Since only water is lost in the process, we can take the difference between the weight of the feed material going into the dryer and the weight of the product coming out of the dryer. So the weight of water removed is going to be equal to the weight of the feed material minus the weight of the product when there are no solids losses. This is equal to 3.5 kilograms of feed minus 0.428 kilograms of product, and we get 3.072 kilograms of water being removed, which we can round off to 3.07 kilograms. The weight of the water removed in this calculation is 3.07 kilograms, which is the same answer as we obtained previously. Now we can revise the diagram to include the amount of water being removed. So Y is equal to 3.07 kilograms. We now know that we will get 0.428 kilograms of product, which is approximately 0.43 kilograms, and we will have to remove about 3.07 kilograms of water in the dryer to do this job. There is a convenient shortcut for figuring out the weight of the final product when you are targeting for a certain final moisture. In the first step, take the final moisture as a decimal fraction and subtract it from 1.00. In the second step, divide the weight of the solids in the initial material by the value obtained in step 1. If you are targeting for a 10% moisture in your final product, the value from step 1 will be 0.90. This is 1.00 minus 0.10, and 0.10 represents 10% moisture as a decimal fraction. So this is really giving you the percent solids as a decimal fraction. That is 90% as a decimal fraction is equal to 0.90. The second sample problem is based on actual personal experiences when I was in the food processing industry working with commercial scale industrial dryers. The scenario in this example has been changed due to confidentiality considerations. A drying process is set up to dry apple slices for use in trail mix blends. The apples have an initial moisture content of 83.0% and must be dried to a final moisture content of 10%. A range in final moisture from 8% to 12% is considered as being acceptable, and this represents the target moisture of 10% plus or minus 2% moisture. On the day that we are considering, the process was started up and the desired operating conditions were achieved. Constant monitoring of the dryer was required, but the operator had to make very few adjustments since the dryer was running satisfactorily. The finished product moisture was right on the desired 10% moisture value. The feed rate to the dryer was 250 kilograms of apple slices per hour. Let's put you in the scenario now as we go to the next step of the problem. About 5 or 6 hours into the drying run, a new batch of apples was introduced into the dryer. These new apples had a moisture content of 84.5%. Knowing that these new apples would pose a potential problem, you spoke to the dryer operator and suggested that immediate measures should be taken to compensate for the higher level of moisture now entering the dryer. The operator looked at you and said there was absolutely nothing to worry about, and he would still keep feeding 250 kilograms per hour of apple slices to the dryer without any changes to the operating conditions. His reasoning was that the new moisture value was only 1.5% higher than the original batch of sliced apples, so he would expect the final moisture to rise by 1.5% as well. This would mean that the new final moisture would be 11.5% instead of the original 10%, but 11.5% was still within the acceptable moisture range of 8% to 12%. The operator said that you were worrying too much about nothing, so you headed back to your office in defeat. A while later, you got a panicked phone call from the dryer operator saying that something was going terribly wrong with the process and that the final moisture of the product was way above specification. Now for the question we need to answer. What was the finished product moisture of the new batch of apple slices? You should express the answer as a wet basis moisture to the nearest 0.1%. You should also note that the moistures here are expressed on a wet basis. There is one assumption, and that is that we may safely assume that no solids are lost in the drying process. As usual, we should begin by drawing a diagram to organize the information that we have been given. The diagram we will draw is for the conditions for the first batch, which is drying satisfactorily. The diagram for the initial operation of the dryer will begin with a rectangle representing the dryer itself. Going into the dryer, we have the feed consisting of fresh apple slices at a rate of 250 kilograms per hour with a moisture content of 83.0% by weight. Coming out of the dryer, we have product at 10.0% moisture, However, we don't know the weight of the product, so we will let that be represented by X kilograms. Water is also being removed from the dryer, and we will work on this calculation in a moment. In most cases, the first thing you should do is find the weights of water and solids going into the dryer. Then you can find the weight of water removed in the dryer and the details about the products. Let's base our calculations on 1 hour of operation. This will allow us to drop the units of hours and perhaps simplify things somewhat. The weight of water in the feed will be 250 kilograms times 83% as a decimal fraction, and we find that there are 207.5 kilograms of water in the feed material. The weight of solids in the feed will be 250 kilograms times 17% solids, or 42.5 kilograms of solid material. We now need to find some details about the product, since we only have its moisture content. We have already let the weight of the product be X kilograms. We can assume that no solids are lost in the dryer, so the weight of the solids in the feed will equal the weight of the solids in the product. The percent solids in the product at 10% moisture will be 90.0%. The weight of the solids in the product can be represented by 90% of X, which is 0.90 times X, and that will be equal to 42.5 kilograms. Solving for X, we find that X is equal to 42.5 kilograms divided by 0.90, and that is equal to 47.22 kilograms. The water in the product will then be equal to the weight of the product, 47.22 kilograms, minus the weight of solids, 42.5 kilograms, which leaves us with 4.72 kilograms of water in the final product from this drying run. So the weight of water removed will be equal to the weight of the water in the feed minus the weight of water in the product. That will be equal to 207.5 kilograms of water in the feed minus 4.72 kilograms of water in the product, so 202.78 kilograms of water are being removed in this drying process. Therefore, the dryer is set up to remove 202.78 kilograms of water on an hourly basis. The dryer being set up to remove 202.78 kilograms of water on an hourly basis will be critical in our solution of the problem, so do not lose track of this value. We now need to examine the new set of dryer operating conditions. So a diagram is needed for the new conditions. So here's the diagram for the new operating conditions, and it's basically the same as we had before, except we're going to change the feed conditions slightly. We still have 250 kilograms per hour of fresh apples going in, but they are now at 84.5% moisture. We have product coming out with an unknown moisture content, and we also do not know the weight. Water is being removed in the form of vapor in this case, and we'll get back to that in a moment. We'll also use a basis of 1 hour of operation at these new conditions. So the weight of water in the feed will be equal to 250 kilograms of material times 84.5% as a decimal fraction, and that gives us 211.25 kilograms of water. The weight of solids in the feed will be equal to 250 kilograms times 15.5% as a decimal fraction, so we know that we have 38.7 kilograms of solids in the feed material. Now we should recall that the dryer is set up to remove 202.78 kilograms of water. So the weight of water in the product will be equal to the weight of water in the feed minus the weight of water that is being removed by the dryer. We start off with 211.25 kilograms of water in the feed minus the 202.78 kilograms that the dryer is capable of removing. This tells us that we have 8.47 kilograms of water present in the product. So the weight of the product will be equal to the weight of the water in the product plus the weight of solids in the product. We know these values are 8.47 kilograms of water plus 38.75 kilograms of solids, and that works out to 47.22 kilograms as the total weight of the product. The percent wet basis moisture in the product will be equal to the weight of water divided by the total weight times 100%. That gives us 8.47 kilograms of water divided by 47.22 kilograms total weight times 100%, and the final wet basis moisture is 17.94%. Therefore, the wet basis moisture of the product is 17.94%, which is significantly out of specification. Now let's add another part to this problem. Using your newly found knowledge of drying technology, explain what is wrong with the logic that the operator has used in his reasoning. You will recall how he said the moisture content of the final product would be 1.5% higher since the moisture content of the starting material was 1.5% higher. For this answer, you need to mention that wet basis moistures are not linear. A wet basis moisture change of 1.5% at high moisture levels involves much more water than a 1.5% change at low wet basis moisture levels. Here are some common traps to avoid in drying calculations, and we will use some of the values that we calculated in sample problem number 2 as examples. Some people say that they have 250 kilograms of feed and they are reducing the moisture content by 73%. They take 83% as the initial moisture content and 10% as the final moisture content, which gives them this value of 73%. So they just take 73% of the 250 kilograms as being their water removal amount. This gives 182.5 kilograms of water being removed, which is totally wrong. So please do not fall into this trap. Other people say that they have 207.5 kilograms of water in the feed and they are reducing the moisture content by 73%. Once again, this is the difference between the 83% initial wet basis moisture and the final wet basis moisture content of 10%. So they take 73% of the amount of water present, which is 73% of 207.5 kilograms, and they use this as their amount of water removal. If you use this approach, it gives you 151.5 kilograms of water being removed, which is also totally wrong. So once again, do not fall into this trap. In summary, in this video, we have examined 2 sample problems that have direct application to drying activities on a commercial scale, even though the weights may seem rather small. Through these and previous sample problems, it should be apparent that dry basis moistures are required for performing calculations on the amounts of moisture lost. As stated in the video on basic drying calculations, before progressing to calculations involving rates of drying and drying kinetics, you should have a thorough understanding of how to do calculations such as those presented here. Thank you very much.